All right, so everybody should be able to at least start this mechanism, right? And it's really easy to get one of these problems, not know necessarily the whole answer, and just get caught up on that and not actually start the mechanism, right? So if you know a little bit, if you know how this starts anyway, you should start it and draw out those steps. All right, so what are we going to do with an acid and an alcohol? What always happens between an acid and an alcohol?
Protonate the OH.
Yeah, just an acid-base reaction. Make water as a leaving group. Right, so pluck a proton from the sulfuric acid. That forms water leaving group at a tertiary center. Right, so that water can leave and form a carbocation. Right, and we're stuck here. Right, you can see we're starting with a 4-membered ring and 7 carbons. Right, we're ending with a 5-membered ring and also 7 carbons. We're not gaining or losing any carbons, but to go from a 4-membered ring to a 5-membered ring to a bigger ring, this has to undergo some rearrangement, right? Some ring expansion. And so, because we're forming a formal carbocation, right, this can undergo rearrangement chemistry, right? This can undergo alkyl shift. So if you look at the atoms that are attached to that carbocation, anything on those atoms has the potential to shift if it forms a more stable intermediate. Right? So on this carbon, right, we have 3 hydrogens. We shift one of those 3 hydrogens over here, we're going to form a primary carbocation. That's not any better, right? That doesn't get us a 5-membered ring, forms a less stable carbocation, right? And so that's not going to happen. Same thing with this methyl group here, right? If we shift one of the hydrides over, nothing's going to happen. We're going to form a less stable carbocation. But if we look at this carbon here, you can see attached to it is a carbon of the ring, another carbon of the ring, and then there's a hydrogen there as well. And if we take this carbon or the other carbon and we shift it over one spot, that's going to give us a more stable intermediate. So if we account for what happened, right, you can see we have a 4-membered ring. So I'm going to start here, 1, 2, 3, 4, right? And then I'm going to number this carbon on the outside, carbon number 5. Right? You can see this arrow, what it's meant to show mechanistically is that carbon 1 is breaking a bond to carbon 4, right? And making a new bond to carbon 5. So here's 1, 2, 3, 4, 5, right? And then I'm just redrawing it up here, 1, 2, 3, 4, and 5. To look like a better 5-membered ring. Right, so we're starting with the tertiary carbocation. What type of carbocation are we making? Secondary, good. So we've learned a couple weeks ago that secondary carbocations are less stable than tertiary carbocations. So why is this allowable? Why would this happen?
The string in a 4-membered ring would be way more unstable.
Right, so when we're thinking about the energy of a the energy that's relieved whenever you do rearrangement, right, or the energy that or energy benefit you get from rearrangement, you can't just think about the stability of the carbocation, but you have to think about the stability of the molecule overall as a whole, right? And so four-membered ring is going to have high bond angle strain, high ring strain. Right? In the tertiary carbocation and in the secondary carbocation, because we're going from a four to a five-membered ring, that ring strain is going to be relieved. Right? So even though we're forming a less stable carbocation center, right, a secondary carbocation center, right, overall energy of the molecule is going to probably come down because of that relief of ring strain. All right, so we're not yet there, right? We have a five-membered ring. You can see we have two methyl groups in the product on adjacent carbons, right? And those two methyl groups in this intermediate are on the same carbon here. So what's going to happen next?
I had one of the methyls from carbon 5 go to carbon 4 through 1,2 methyl shift in order to form a lower energy tertiary carbocation.
Excellent. Yeah. Right, so we got to a secondary carbocation, and we can further stabilize this intermediate by doing another alkyl shift. In this case, shift one of the methyl groups from carbon 5 to carbon 4. And then the last step to get to the product, so we will take one of our alcohols that we started with at the beginning and just use that as a base. Let the proton and form the elimination product. Questions about this? Is anybody unable to follow? You're all super quiet. All right. So what we'll do for the rest of today is we're going to finish up chapter 14, looking at epoxides, and I'm kind of reviewing amine chemistry. Okay, so related to this, what we just did on the board somewhat, we're going to take a look at epoxides, which are three-membered rings with oxygen in them. Right? Simplest epoxide functional group is called oxirane. Right? It's just a three-membered ring, two carbons, one oxygen, four hydrogens. Right? But generally, right, that three-membered ring is seen as part of other, or seen as a functional group as part of other molecules. As you can imagine, there's a lot of ring strain that is seen in three-membered rings with oxygen, or three-membered rings in general. And that's what makes this functional group reactive, one of the things that makes this functional group reactive. Right, so first off, I want to look at substitution chemistry of epoxides. And I want you to take these two reactions, starting with the same starting material. Right, you can see that one of these reactions is being carried out under acidic conditions. The other reaction is being carried out under basic conditions. Right, so I want you to take 5 to 10 minutes, see if you could figure out what the product or the major product in each of these reactions is going to be. Right, think about it mechanistically. Right, what is going to happen, how probable or how likely an interaction will be. Right, what the most stable intermediates, if there are going to be intermediates in these reactions, what those are going to be. Talk to each other, and we'll go over this in about 5 minutes. Remember, we're focusing on substitution here, right? That's why in these reactions I've tried to indicate colder temperatures. So we're favoring substitution chemistry. So that's reasonable.
Because the first reaction is going to happen, that oxygen is going to be released. So she's going to do it as soon as. Assuming that the ball breaks. I guess it could be better, but I think that would be the height of the lowest one. And then I don't know about that. Can't think I could also grab a hydrogen and then acid again. Maybe either way, I think that's safe. But
Yeah.
obviously, not a professional. This one's.
So it forms the OH first, but then is this bond break?
So that's the idea, right? You have two. All right, folks, let's go with this. So it looks like some of you are on the right track, at least starting out. All right. Before we get into the mechanisms, I want to go over ring strain, talk really briefly about the properties of epoxides, which hopefully should be pretty apparent. All right. So ring strain, remember, happens whenever bond angles deviate from the ideal bond angles. Right. So sp3 centers, the ideal bond angles are going to be around 109 degrees, 109.5 degrees. Right. And so when we deviate from that ideal bond angle, usually by large amounts, right, we develop ring strain. And so if you look at a three-membered ring, the internal bond angles of that three-membered ring are going to be 60 degrees, right, just based upon having an equilateral triangle. And that obviously deviates pretty greatly from the ideal 109.5 degrees. All right, how that's manifested physically, right, if we think about bonds being formed by the overlap of atomic orbitals, right, this represents good orbital overlap. When those orbitals are pointing right at each other, right, and they're going to overlap effectively, so you form a strong, in this case, strong carbon-carbon bond, right? But those orbitals have to point at each other and have a really good handshake. If those orbitals aren't pointing directly at each other, they can still overlap, right? But they're not going to overlap as effectively. So in this three-membered ring, we can imagine the orbitals are coming off of the atoms at the right angle, right? But they're not going to be pointed at each other because there aren't enough atoms in that ring for that to happen. So we get overlap, right? But it's not ideal overlap. And that's going to result in weak bonds, right? Or high energy bonds. Okay, so if we were to take propane and combust propane, right? And compare that to the combustion of cyclopropane. Cyclopropane is going to give us more energy because its carbon-carbon bonds exist at a much higher energy level than just regular propane, right? And so what that means from epoxides is that we have these weak carbon-oxygen bonds, all right? Those weak carbon-oxygen bonds are polarized towards oxygen because oxygen is the more electronegative atom, right? Which makes the carbons electrophilic. And if we add a nucleophile to those carbons, we have a good leaving group in the oxygen, because that's going to pop open the ring and relieve a lot of ring strain. Right? So thermodynamically, it's a very high energy group that when it reacts is going to get us down to a lower energy level. How it reacts in a lot of situations is going to determine what product to do. So here again we have two substitutions. You can see that in the substitution reagents, right, both involve methanol. Right, here methanol is going to be more of a solvent, right, and methoxide, the basic form, will be the nucleophile. Right, up here methanol will be the solvent and the nucleophile, right, the one under acidic conditions. Right, so let's go through the mechanism really quickly. Let's look at the acid mechanism first. Right, so we're going to start this off by taking the oxygen of the epoxide, protonating it. Forms a cationic intermediate. Now this is going to be very prone to break open, right? So we, just like with carbonyls, when we protonate the oxygen, the bonds leading to that oxygen's pulling harder on those electrons, right? So it's going to really, really polarize these carbon-oxygen bonds, right? And so this is going to want to pop open. And it could pop open in two different ways, right? We could break carbon-oxygen bond on the left, or we could break carbon-oxygen bond on the right. We break the carbon-oxygen bond on the left, that's going to give us a really high-energy primary carbocation, right? We're going to form a carbocation on this carbon. And that's not, as we've seen in substitution, right? That doesn't happen, right? If we break the other carbon-oxygen bond, right? You can see that's a tertiary center, and so that's going to give us a tertiary carbocation. So we'll break the carbon-oxygen bond on the right. Forms a tertiary carbocation at the center, and then methanol can add in and after a couple steps we're going to get this methyl ether. Right, so under acidic conditions for epoxides, right, the mechanism is going to proceed in such a way that it's going to create a carbocation, and the carbocation is always going to form on the carbon that can better stabilize that charge. Right, so in this case, if we look at this, the nucleophile will add to the more substituted carbon of that epoxide. Right, so if we think about basic conditions, here we don't have an acid, right? So we're not protonating the oxygen. And so we're not forming carbocations, right? That oxygen's not going to just leave the epoxide, it's not going to break open on its own without protonating the oxygen first or activating it somehow, right? So we have a base or a nucleophile in this case, and so where's that nucleophile going to go? Right, we have two electrophilic positions, right, based upon the the reactivity of epoxides. So where will that nucleophile go? Yeah.
On the left.
Why?
Because it's going to be easy to overlap.
Good, right? So if we think about orbital overlap, right, in both cases, if we're doing an SN2 reaction, right, we have to overlap with the carbon-oxygen sigma antibonding orbitals, right? So just like in SN2 chemistry, right, the nucleophile is always going to go to the more available carbon, right, primary methyl, sometimes secondary carbon, but substitution never occurs on a tertiary carbon. Right, so in this case, the methoxide will add to the more available carbon. We'll open that remembered ring. And then just to finish this off, we'll use the solvent as a protic source and protonate the alkoxide. Right, so the rationale in this case is that the nucleophile is just going to add to the more available set or more available sigma antibonding orbital of that epoxide. Right, just like we would expect for other SN2 substitution reactions. Right, so it's a kinetic case, right? It's just a lot faster on this side and a lot slower on the other side. We need more activation energy. Questions about this? Okay, what if we change this up one more time? This will be the last thing we go over. How will the reaction be affected if we use terbutoxide and terbutanol? Right, so still basic conditions, but we're obviously changing the structure of that base significantly.
Become an SN1.
Is it the same temperature?
Doesn't really matter. Yeah, it doesn't really matter.
That hurts me more.
What's that?
It hurts me more if it doesn't matter. I thought it hurts me.
So, yeah, it's not gonna really matter. I mean, it will matter in the reaction in terms of the rate of the reaction, but outcome it won't matter.
Is it gonna do an elimination?
Good, good, yeah. So remember, this is a non-nucleophilic base, right? A stronger alkoxide base. So this is going to result in an elimination reaction. So the product that we should expect is going to be this product, right? So, sulfur. right? So we have 2 protons on this carbon, would be the same as these 2 protons on the carbon at the top of the 5-membered ring. Pull one of those protons, electrons will fall down, right? And then we'll break the carbon-oxygen sigma bond, right? Not carbon-carbon sigma bond, but polarized carbon-oxygen sigma bond. And then we pluck a proton to get to the alcohol at the end. Questions about this? Okay, so epoxides, really unique electrophiles, right? Can undergo substitution chemistry and undergo elimination chemistry as well. Questions? Is that clock accurate up there?
2 minutes more.
2 minutes more. That's about all we want to go over. Much 2 minutes, so we'll end there. So exams Wednesday night. It's going to covers chapters 12, 13, 14. It will, we're just learning epoxides today, so expect epoxides to be on it, but it'll be featured very lightly. Workshop, so I'm going to move Tuesday, was tomorrow night's workshop, I'm going to move it to tonight. Okay. In this room, I'll double check, but I think this room is free. And then if the TAs want to have another workshop tomorrow night, then they can, I'll give that option to them. But otherwise, the last workshop before the exam will be tonight. Okay. Questions? Okay. See you guys tomorrow for lab, or tonight for workshop.